of several variables with Anna Kimaczyńska, which will talk us of the grad div operator.
So first, recall some facts. Let's V be a vector space over R. The dimension of V is n. For k from 1, 2, and so on, the space of all k linear mappings is called the space of k tensors over V and denoted here by star k. We also accept the convention that star 0 is R. A k tensor phi is called symmetric if phi of V sigma 1 to V sigma k is equal phi of V1 to Vk for all vectors V1 to Vk from V for any permutation of the set 1 to k. The space of all k-symmetric tensors will be denoted by Sk. Its elements will be called here shortly k forms. We accept the convention 0 is R. Symmetrization is the linear operation from T star k to T star k defined by following equation. And we have the properties of symmetrization. It is a projection, so sim square is sim, and image of sim is Sk. In particular, symmetrization is the identity on Sk. Assume that V is, it must be that. Assume that V is equipped with a scalar product. The scalar product can be transmitted to star k, to the space of k tensors by the formula. we have such formula for tensors, k tensors, where E1 to En is an orthonormal basis in V. Sk as a subspace of T star k inherits the scalar product from the ambient space. In addition, the scalar product in Sk times V is given by such equation where phi is from Sk and Vw is from V. In Sk and Sk times V, we here consider also another scalar product. This scalar product is given by the previous one, and we know by that symbol that's symmetric multiplication of symmetric tensors. Operation of substitution of a vector V is defined as the mapping from Sk to Sk minus 1. It is given by such equality. We put vector V on the first base. If k is more than 0, if k is 0, it is 0. And we have the following proposition. IV of phi times psi is IV times psi plus phi times IV phi. And we define another operator for k from 0, 1, and so on. The operator A from Sk to Sk minus 1 times V by the equation A phi is the sum from 1 to n I EI phi times EI, where E1 to En is an orthonormal basis in V and phi is from Sk. The trace operator is the operator from T star k times V to T star k minus 1 in the bundle of vector forms, and it is defined by the following formula: trace phi times x is equal ix phi. And this is the trace operator for vector value forms. And another trace operator from T star k to T star k minus 1 in the bundle of scalar forms is defined by the formula tilde trace phi is the sum from 1 to n iei phi, where E1 to En is an orthonormal frame of V. Now, assume that all objects and morphisms are smooth. It is of class C infinity. Let M be an oriented manifold of dimension n. Consider now vector bundles over M instead of simple vector spaces, since vector bundles can be treated as vector spaces parametrized by points of M. Symbols used in the previous section for denoting vector spaces will be used now for denoting suitable bundles. Denote now C infinity of M, the ring of smooth functions on M, and T is M, T star is T star M, and these are the tangent and cotangent bundles respectively. And denote also T star K equals T star Km, the bundle of K tensors on M, and Sk equals Skm, its subbundle of K-symmetric tensors K-formed. For any bundle E over M, denote C infinity of E, the C infinity of M module of sections of E. Let Mg be a Riemannian manifold for any P from M. We have such scalar product in Tp, where it denotes the tangent space to M at P. And we have here the Levi-Civita covariant derivative of the metric P, given by these conditions. We have here torsionless and compatibility with metric. Let nabla be the Levi-Civita covariant derivative of the metric G on M. The following formula for phi from C infinity of Sk and x1 to xk from C infinity of T transmit such nabla to the bundle Sk. The extended connection is denoted by the same symbol, and we use the convention that we put here from the first place. Obtained covariant derivative may be treated as such map from C infinity of Sk to C infinity of star times Sk. Now define we defined the symmetric derivative operator. This operator is from C infinity of Sk to C infinity of Sk plus 1, and it is given by ds equals k plus 1 times symmetrization of nabla. The local form for the symmetric derivative is described by the following. Let E1 to En be a local frame of sections of T, and E1 star to En star be the dual frame. Then locally we can express ds as follows. We can extend ds to the bundle Sk times T as follows. Define the operator ds from C infinity Sk times T to C infinity Sk plus 1 times T by this following formula, where nabla x is treated here as one form with values in T. And we have similar local property. We can express locally ds by such equality. Let now E be n vector bundle over M, and we have a scalar product in E and define the global scalar product. So by this symbol, we understand here this global scalar product. And we have here another scalar product in the bundle Sk, which is given by this equation, similarly as for this scalar product. So now define the gradient operator from C infinity of Sk to C infinity of Sk times t by gradient equals A ds minus dsa. This operator is a differentiation of the algebra of symmetric forms in the following sense, and define the divergence operator from C infinity of Sk times t to C infinity of Sk. Divergence equals trace ds minus ds trace, and it has similar property for phi from C infinity of Sk, psi from C infinity of Sl times t. We have divergence of phi times psi equals phi times divergence psi plus gradient phi times psi. And we have theorem: the differential operators minus gradient and divergence are formally adjoint to each other with respect to the global scalar product, the second global scalar product. The composition of these two operators, divergence and gradient, is a second order differential operator diff grad from C infinity of Sk to C infinity of Sk. These all operators were investigated in detail in my PhD dissertation. So let's now consider the composition of operators gradient and divergence. And this composition led to a second order differential operator grad diff, and it is from C infinity of Sk times t to C infinity of Sk times t. The second order differential operator grad diff is the following sum of differential operators: g1 minus g2 minus g3 plus g4, where g1 is a ds trace ds, g2 is a ds ds trace, g3 is dsa trace ds, and g4 is dsa ds trace. We have some properties. Let phi times x be from C infinity of Sk times t, then trace ds of phi times x is divergent of phi times x plus ds ix phi, and ds trace phi times x is ds ix phi. At E1 to En be a local orthonormal frame on M, and let E1 star to En star be the dual frame, then locally A ds phi is the sum from 1 to n nabla ei phi times ei plus the sum from 1 to n ej star times phi ei nabla ej phi times ei. And dsa phi is the sum from 1 to n ej star times iei nabla ej phi times ei plus the sum ej star times I nabla ej ei phi times ei plus some ej times ej star times I ei phi times nabla ej ei for phi from C infinity of Sk. And we have the theorem: the differential operator grad diff is formally self-adjoint with respect to the global scalar product. This second global scalar product. And this is all. Thank you very much for your attention.